In this video, we'll cover the problem course schedule. Here we have a series of courses we need to take. So n tells us how many courses we need to take. In this case, it's 2. And there are also some prerequisites. So this, for example, tells us that you have to take course 0 before you take course 1. And we want to figure out if it's possible to take all the courses that we need to take. For example, if you look at this case, we need to take 1 before we take 0, but we need to take 0 before we take 1. It's impossible to even get started. Really, this problem is just kind of a hidden cycle detection problem. The only case where it's impossible to take all courses is a case where there's a cycle in our graph. There's kind of some set of courses that are dependent on each other such that it's impossible to even get started. None of those courses can kind of be picked off and allow us to start taking some of the other courses. So really, we're just checking if there's a cycle in our graph. And the way we do this is we basically, there are many ways to do it. One way is with a depth first search, which is basically we start from every node. When we get to a node, we're going to try to traverse all of its neighbors. And we're going to mark our state. So we're going to say I'm currently visiting this node. If I ever go visit neighbors and I somehow come back to this current node, this one that is currently being visited, then that means there's a cycle. I left myself and I came back to myself. So we're going to check all of our neighbors. If we never do that, then we're going to mark ourselves, instead of being currently visiting, we're going to say previously visited. And I think this will become a lot clearer in code. So let's go ahead and code this out. So we'll have our number of courses here. We will say, iterate through each course. So we'll say course equals, or we'll do course num equals 0, course num less than num courses, and then course num plus equals 1 here. And then I guess there's some other boilerplate we need. We're going to need a graph here, which we'll build a graph from our prerequisites. And then in the end, let's see, how are we going to do this? Yeah, we'll come back and we'll write the logic inside in a moment. So why don't we write our build graph? And now that I noticed this, let's change the function just to be consistent. So we have our arrow function. Okay. So here we'll take a list of prerequisites. And remember, in a graph, we want to know from the current node, where can I get? So in this context, that means when I complete a class, what classes have I just freed up, at least partially? So we'll have a node and then the prerequisite node. So that's kind of the node that comes right before the current node. Node depends on prerequisite. You must first take the prerequisite class to take node, which is the current class. And note I'm writing it somewhat generically so that this doesn't have to just be for classes. So we can say we want to do graph at prerequisite dot push node. We're saying we can get from the prerequisite to the node, but obviously we have to make sure that we can do this. So we'll say prerequisite in graph is going to be graph.hasOwnProperty, the prerequisite, and we'll say if the prerequisite is not in the graph, we're going to set graph at prerequisite equal to an empty array. Okay, now that we have our graph, what we will do is we'll say go to every class. Actually, before we do this, we need a visited array. So I'll do an array that is of size num courses here. And we're going to have 3 states, and I'll define them up at the top. We're going to have unvisited, which we'll have just as a 0. We'll have previously visited, which will be a 1. Doesn't actually matter what these numbers are. And we'll have a currently visiting, which will be -1. Of course, these numbers are arbitrary. They could be anything. The key is that we have unvisited, currently visiting, and previously visited. Initially, every node is unvisited. Now, when we come here, we're going to say here, well, first of all, if we've already visited a node, we don't need to visit it again. So we can say if visited at the course number is equal to previously visited, we can continue. Otherwise, we want to check if it has a cycle. So we'll say has cycle is going to be check if has cycle. We'll pass in the graph, we'll pass in the current node, which is course num, and we'll pass in the visited set. If we do have a cycle, we can just return true, or I guess in this case return false. It's not a valid course schedule. Wait, hold on. Yeah, okay. So we return false. We say there's a cycle, we cannot complete all the classes. And then as our default, if we go through everything, we can return true and say, hey, we never found a cycle. It is possible to go through the entire graph. Here, we can write our check if has cycle function. This one we can write generically. It doesn't have to be specific to courses and anything like that. It's just given a directed graph, check if there's a cycle. Now this is going to use a DFS, so it's going to work recursively. We'll have our 3 steps, our base cases, our process node, and then recurse on neighbors. So for our process node, we want to say the current node is currently visiting. So we're going to say, hey, I'm currently visiting this node. Then we're going to go through all of our neighbors and see if we somehow get back to this node or some node that is currently visiting. So we'll say neighbors is going to be graph at node. And then we'll say iterate through each neighbor of our neighbors. And what do we want to do? Well, we'll see if it has a cycle by doing check if has cycle. Remember, we magically pretend this is going to work and give us the answer that we want, and we don't have to think about how. We know if there is a cycle, immediately we know, okay, there is a cycle, so we can return true here. And then as our default, we will return false if we check all of our neighbors and we never find someone who has a cycle. Okay, so this is the core logic. The only thing that remains is how do we terminate this recursion? How do we know that we've found a cycle? Well, the first thing is if we have found that we are currently visiting this node, we know that there's a cycle. So we return true. There is a cycle because we already marked this node as visiting and somehow we got back to that node and we're going to try to mark it as visiting again. There's one step that's actually missing, but we'll come back to that. The other case is that if we have a node that has already been visited, so we'll say previously visited, then we can return false because we know, hey, we already came here, we didn't find a cycle. And the key is that we need to mark the current node right here as previously visited. Because here we said it's currently visiting, then we went on all the neighbors, we're about to finish. We're going to return out and say, hey, we're done. So we should say we're done visiting this. So if we get to a node that has been previously visited, we already checked that, there's no cycles there, we don't need to worry about it. Now there is one small case that doesn't matter for this problem, but it's good to think about. If you return true, you will never set visited a current node to be previously visited. It'll be stuck in currently visiting forever. For this problem, it doesn't matter because when you return true, it's going to bubble all the way up. It'll, maybe come back here, and then that'll be true, and it'll return true all the way up to here, and then we're just going to return false. We never actually use the visited anymore. However, it would be a bit better to write it in a way where this doesn't matter. In any problem where we might actually be using the visited in the future. So just be cautious of that. If that was the case, you'd probably have a Boolean variable up here that you default to false. If this is true, you overwrite it to true, and then you just return that Boolean here. So you don't kind of terminate early, and you still do access the visited at node equals previously visited step. Okay, this should be all the logic that we need. So let's go ahead and see if this is going to work. So if we run our tests, let's see if there's any bugs. Okay, looks like there are bugs. Const neighbor of neighbors. Yeah, I was thinking this might be an issue. Okay, so here we're trying to iterate over our neighbors, but sometimes node is not in graph, so then we get undefined. So first of all, we're going to check if the node is in the graph. Sometimes the current class has no kind of classes that it enables. It has no classes that have the current class as a prerequisite. So in that case, we would get undefined when we do graph and node. So what we're going to do here is we're just going to say if the node is not in the graph, we need to wrap up. The way we're going to wrap up is doing these two lines. So we're going to say here, mark the node as previously visited, and then just return false. Or actually, we can do this a little bit more cleanly because we can move this to the process node step. And that way we never even need to set it to currently visiting. So what we can do is we can do this. You could also consider this a base case if you wanted to. I guess that might actually even make more sense. So this way, we're just saying if there are no neighbors, then obviously there can't be a cycle here. There's nothing to explore, so just return false immediately. That should fix our issue, hopefully. Okay, looks like that does. So this was course schedule. This is kind of generic cycle detection in a directed graph. That's all for this video, and thank you for watching.